Sure,
right?
Leela. Yeah.
So we're going to talk about well-architected ML platforms. I mean, this seems like a self-complement, right? Well-architected, right? But we'll talk deeper into it. So this part, I don't think I have to explain to anybody who's done some data science, right? You may have heard about CRISP-DM, model building, model management, right? You start with a goal, you have understanding of the business or domain, data understanding, preparation, modeling, evaluation, deployment, and maintenance. Up to here, pretty much everything is normal. These three are interesting. Sometimes you have outliers within data, and you have to make sure the algorithm doesn't fall off and predict something erratic, right? I'm sure you have come across some outlier analysis. Then the other part is model regression. What happens when your model is supposed to figure out pictures of cats from YouTube and now it's figuring out dinosaurs? And the next thing is about recall feedback. What happens when there is recall? So, our goal is essentially to take business understanding, data understanding, modeling, evaluation, and come back to business understanding, because data keeps changing, your business keeps changing. For example, I'm working with multiple large companies in terms of the prediction of various economic factors due to COVID. There is no algorithm that could predict the effect of COVID on sales forecast, for example. Right? A lot of companies are busy doing that now. And some of them don't even have risk averse models, right? They have models that can predict a few things, and they have not factored in things like recessions or COVIDs or, sudden dips in profitability. So that's where the actual production use of machine learning comes into play. That's where data scientists are actually challenged. Okay. So with that, we have set the context. Now we'll see what is needed to actually understand and explain that, right? Uh, Obviously, like all things, building the basic version is easy. Building a robust and reliable and performant version becomes harder. So what does well architected mean? Right? This is essentially the topic of the presentation. Interestingly, it's not something that I coined. It's coined by AWS, which is Amazon Web Services. Some of you may have heard it. Well architected for anything, for software, for real architecture like buildings. Essentially, well architected means you have taken care of some things. You haven't just prototyped it one afternoon and put it into production next day and wonder what happened. Right? And real industries go all the way to like Six Sigma and other processes. But you look at cloud-based frameworks or something like software machine learning frameworks, we have to still question whether they are well architected. So the first thing is about operational excellence, right? There's a famous saying um, in software and also more popular with data science these days. It's called it runs on my desktop, right? With the data in my Excel sheet, when I train it, it works amazing. When you go to production, there is a lot of surprising data, so the algorithms start to regress. And not just that, data is messy and unclean. You would expect a nicely formatted Excel sheet, but a lot of times you get garbage also. So you need operational excellence to prove that the piece of code that we're deploying is reliable. right? It has everything that is needed to be able to monitor and understand how it's performing. The next part, I don't have to explain much. It's security, right? Even Facebook doesn't is not an exception. If you touch topics like data privacy or security, right? So essentially, you need to make sure the data that you're using within algorithms is secured well enough and also biasless. This becomes very, very, very hard. I know a lot of Silicon Valley companies which are now struggling to prove that their algorithms are not biased towards a particular race of individuals or a particular economic group or a particular choice. I'll give you an example. Sometime back, there was research done, and someone found if you're booking airline tickets and you book them from a MacBook, they actually cost more. Okay, this is actually pretty hard to believe. Like, how does my laptop impact the ticket rate? Because at some point, people have deduced, like the data scientists, good for them, they've deduced Mac users tend to spend more. Maybe if we offer them a slightly higher price, we will still get away with it. They tend to line up at Starbucks with their Macs, so they must be willing to spend more money. But if you look at it, it's actually a user or consumer bias. So there's a lot of security and privacy that needs to be handled once you build the model, in short, right? Not to mention, how do you shelve this data? Where do you put it? Whether it gets leaked? Those are infrastructure level concerns. I won't even mention them because they should be already taken care of. By the time data gets to our hands, it should be already secure. I'm talking about algorithmic bias and causes that will borderline get into regulation and privacy. Okay, let's park that aside. Next, we talk about reliability. So I built this algorithm. Sometime back, we had an interesting challenge. I built this algorithm where I'm looking at a specific camera, and the images are drivers. Essentially, they are driving, a truck or a bus, something like that, and we have to understand the cabin conditions, but we should not expose the driver's face. Okay, so this is again related to security and privacy. So basically what we said is, oh, that's cool. We'll build a CNN that identifies faces, reverse complement it, and simply mask off faces. Oh, wow, we could do really cool stuff. There's only one challenge. This algorithm runs at like 4 frames a second. And we were getting like roughly around 250 to 300 a second. So that means you have to run the CNN in at least order of magnitude higher copies, which means your algorithm should be reliable enough. If it fails, it should be able to automatically come back. It should be parallelizable. It should be deployable in a setting where the workload is very, very bursty. And that takes us into performance and efficiency. Okay, we've switched up everything. We've used 100 servers, not one, not two, not four, 100 servers. Then the impact is in cost, right? We can't really simply use 100 servers. Somebody has to sign a check. And if that is you, it's even harder, believe me. So essentially, you want your ML platform to have all of these properties, none of which are actually guaranteed by data science. They're all guaranteed at the perimeter of data science. Okay, no worries. We'll keep digging into what it takes to build something like this. And by the way, I pasted a link here because these are some excerpts from um, AWS infrastructure, and that would be a very interesting read for you guys to understand. Right? Someone told me, and it's almost like a famous quote, right? A data scientist is a statistician who's good at software engineering, and a software engineer who's good at statistics. So this is the software part of data science that we have to be understanding. Move to the next one. Same thing, different tune. What does production mean for an ML platform? Right? And this day and age, again, having spent a decade on building these platforms and putting real data science workload, this is what we learned. First thing, you never know when you need scale. So you need auto scaling. Today we'll say, okay, we are predicting, which costumes are better, and suddenly the algorithm takes off. Everybody is buying based on your prediction. Now you want to scale it across all branches. Now you want to scale it across all age groups, all demographics, what have you. So that translates back into scale. And when it comes to scale, you have to use cloud because you can't scale your data centers physically. If you want to build 100 nodes, it takes 3 to 6 months. And not only do you have to scale infrastructure, you also have to scale all the other services. For example, you are pulling data from somewhere for feature engineering. Now that has to scale. All right. The next part is collection and curation cannot be ad hoc. It has to be very structured. I've seen a team of 60 data scientists. They all build algorithms, very sportive, very communicative, very competitive as well. What we noticed over some time is there are redundant algorithms. One algorithm predicts profit and loss, the other algorithm predicts profit, loss, and also operating budget. Which one should I use and where? And one algorithm uses specific data from 3 sources, the other one uses granular data that is parsed from 36 different sources. So I hope you see the gravity of the situation. Machine learning and data science, because it's primarily research oriented, it quickly gets out of control with traditional software engineering builds. And the third one is self-service training, experimentation for forecasting and simulation. Uh, this is again super important. You want data scientists to be autonomous. They should do their own research. They should be able to use their own algorithms. If they want TensorFlow, they want TensorFlow. If they want GPUs, they want GPUs, right? So you can't take self-service out of research. You can't take the exploratory analysis out of data science, but you need to still keep it structured. That's fine. We'll be able to manage with that. The next parts 4 is ML as a service model. This goes back to my face masking algorithm. Again, similar way, I've made an algorithm that can predict whether a stock goes up or down. But too bad it's only on my laptop, right? I need to make a website for it. I need to be able to make an API and call it and then give it to my customers so they can predict. And when their stock goes up, they'll give me a commission. So suddenly you need all of software engineering to deploy your model, right? Of course, you could do that with Python Flask or a few things which are very close to our data science when we do most of it. But this is a key area where a lot of data science teams fall short of. Oh, now we want somebody else to build the service, right? I've done my research, I've trained my algorithm, everything works fine, I've cross validated it. I just don't know how to put it into a service that is callable and make an API out of it. The last part, again, a repetition of what I said before, prediction performance and feedback from drift. This goes back to my sales example, right? Yeah, I was able to successfully predict 4% of the prospects are converting. That's good. But when it drops, you don't want business to tell you that. You want to find out. So if you look at these as platform capabilities, bottom up, you get what are the benefits, right? So you need platform as a service, database as a service. You need some identity access management, security controls, some kind of data lake. There's a lot of marketing buzz around data lakes, right? And then you need insights, which you will get from a lot of data scientists. However, the key is from all of this, if you make a decision that actually has significant business impact, then the platform is justified. So this is the interesting part of data science compared to other software. If you build a website, you have the website, everything is fine, you have a product. Think of an ML product. You built a prediction service. Somebody has to predict something with it, and the prediction should come true and they should benefit from it. More or less like a retail website. Yes, I built flipkart.com or amazon.com, but somebody has to come and buy something. So unless the algorithms are actually in production as services that are consumable and impacting business decisions, they remain research. So productizing ML is super important, right? This is where the goal definition comes into play, right? What is our goal and how did we achieve it with the ML exercise? We could talk a little bit about how did we get to these. Essentially, there is Amazon ML stack. If you are familiar with it, that's fine. If you're not, it's important to at least find out what these are, because whether it's Amazon or something else, there will be a cloud platform. You will be using some of these things to be able to train and deploy. And why did I pick something in the cloud? Why didn't I just say use R or Python? That should be fine. If not, we'll use Weka or Statistica or Data Miner or something else, right? Because they all tend to be personal interaction tools, right? They work to the extent that your exploration happens. They don't work when you want to deploy your model and see business productivity. So if you know Python, if you've used Jupyter Hub, then you would want to go and try SageMaker to leverage how to deploy your Jupyter Hub notebook onto a SageMaker based GPU instance. If you want to extract data, you want to use something like EMR or Kinesis to be able to get streaming data and train your model with SageMaker. Right? These are important as you go through your education and preparation for the industry. And if you're doing something much more advanced like vision or speech, these things become fundamental. They're almost needed because you can't do general purpose text mining today or general purpose computer vision without any of this at scale. At scale is the key. Like I mentioned, yes, I can mask a face on one photograph pretty easily on my desktop. When I'm getting 250 images a second, I need something else. So how do you build your same solutions that you have done with an Excel sheet on a desktop, or maybe if I'm being too trivial, with a data set on an R server or a Python server, or even use something like Hadoop or Spark into a reliable data pipeline, into a reliable ML pipeline. So this is one architecture. There are ways to use Lambdas, which are serverless functions in AWS, or you could use EC2, which is basically a server in the cloud. But if you notice, there is a specific cycle for your pipeline. So you ingest data, then you model it, and you store the data into an S3 bucket. Then you enhance it again, and then you start doing transformations, feature engineering, training. You have serialized models that can go to SageMaker. And from here, you need to expose web services, which will do historic requests or forecast requests. So your ability to build something like this, once you have mastered it, the good thing is it doesn't change once you have mastered it, right? Once you have learned how to write a Lambda, you're good. You don't need anybody else to deploy your feature engineering code. Same way, once you're able to spin up things, by the way, all of this can be done with free accounts on AWS, right? I'm not sure how much you've been looking at cloud-based ML, but it's almost a de facto now in several cases. And there is an industry standard term now for this. It's called ML engineering or ML ops, right? Data science is one side of the game. Data science is already 10 years old, right? Um, there's all kinds of phrases about how it's coined and how it is, the most sexiest job of 21st century and all of that. But now we are getting into the next decade, 2020 to 2030, where ML will be commoditized. Think of it like building a website. In 1999, it was the coolest thing to do. Today, building a website is just a necessity, right? We are getting into the next phase of ML where you need reliable ML ops, you need reliable ML engineering. So this is one pattern of architecture. Now I wanted to show something much more deeper, like true architecture from somewhere, unknown source. So you can see there are several data sources. There are customer marts, risk marts, sales, accounts, Salesforce data, some SaaS data, clickstream, speech, telematics, all kinds of data. You have 250 databases. And you're going to pick that data and use some kind of Jupyter notebooks, something like Spark for distributed processing if you need to process a lot more data. And maybe come up with an algorithm. Maybe use 1,000,000 rows, 2,000,000 rows, carefully feature engineering it. From here, the game changes. You have to commit your code to a code repository. I guess you're all familiar with Git now. And you have to commit your model and data. This is something most often forgotten, right? Everybody says, I have a model. When I ask, where is the training data that you used for this model? And have you versioned it with the model? That's where we start to see gaps. If you train the same model with a different set of data, then you don't get anything out of it. So how do we version our training code along with the training data becomes key. So we started building something called model registry. There is an open source component called DVC. If you've not heard of it, you should actually Google it and try it. And then you want the training and validation. Like I said, the key phrase someone told me is, it works on my desktop. Sorry, that doesn't help. It should work on our training and validation framework. We'll take that model, we'll use the same data at scale, and we'll run it kind of in an industrial fashion. We'll tell you if it works again. So typically that is done using some kind of ML orchestration framework like ML flow. You could build it out of, K9 or other things also if it is a smaller shop. But, these days, ML flow is adapted by Databricks, and SageMaker has ML pipelines as well in AWS. So in whichever way, basically, it's not going to be the data scientist who's going to train the algorithm. He trains it once on his desktop, maybe on a larger server, and he pushes it over to a different team that runs ad hoc training. Right? So that's where it will be tested. I'll give you an example. One of my colleagues works in Bing, and essentially he comes up with a better way to search for something. He says, okay, if I use the search algorithms this way, I get best search results. That and all is fine. How do you prove it? Oh, there are 50,000 popular searches. We'll submit that code to a pipeline, and all those 50,000 popular searches should retrieve better results than what they are currently retrieving in production Bing. You see what happened here? So whatever we customized and claimed to be almost proprietary suddenly becomes commoditized. And not only that, that model will be deployed and it will be used for prediction, and they will tell us the prediction performance. We can't say, yes, my model is 87% accurate, the rock curve looks amazing, right? So essentially, there are production pipelines that will be doing all of this. And we've learned this the hard way, believe me. We've actually taken algorithms that have been built, taken them to production, had to pull them back, and then retrain them. That's another hard part. Okay, I trained this algorithm on a huge set of data, like 20 terabytes. Now, to train it back, it takes me at least 3 hours if I'm using 100 machines to train it. But if I have only 10 machines, it's going to take a week. So you need an entire framework, and the sooner you understand these parts, the better you'll be to accustom to it and fall in place. And once you fall in place with the process, it'll become that much easier to actually do data science. So let's take a different perspective at it. So, we say, oh, we got some data and we trained the algorithm. Now, with respect to governance, there will be several different departments within your organization that will ask various questions. First of all, where did you get this data from? Can you get it every day? Is it in a consistent format? Do you know that it follows governance and privacy regulations? So I'll give you an example. Somebody said, oh, I can predict car sales by zip code. Car sales by pin code seems good. Okay. Yeah. So that means if the customer has provided an address and you see a particular pin code, you can predict the likelihood of buying a car. So far, so good. If I email everybody in that pin code repeatedly, someone will buy a car. But there is a downside to it. The downside is you are now actually making economic choices by demographics, right? So that means there are areas where you will not be interested in selling cars. And that gets into all kinds of politics. So to keep it short, we have to understand how we have obtained that data. And can we repeat that process? And can we comply to data governance, not as an afterthought? So now we've talked so much about all of this. Wow. We said it should be this way, that way, right? How do you build something like this? Right? We've written a book about how to build these platforms. Now we have to start building them. And a lot of teams, so they have been using R, SaaS for maybe 20, 30 years in several companies, right? So how do you take them into an ML platform? So this is where a lot of teams fail to adopt ML. In the end, the statistician says, no, it's still not better than the hand-coded equation that I wrote when sitting on a bench with a mathematician, right? I've really seen these stories. So essentially, you want to be able to plan for advanced analytics as a platform, right? And it's going to touch every part of your business. So you need to be able to understand how you build it, come up with milestones, come up with infrastructure for it, come up with governance for it. Of course, I'll leave that aside for the leaders, and then you would actually evangelize and adopt it slowly. So this is a common case, right? I have a SaaS algorithm that's written 15 years ago. I've seen this so many times, believe me. And now I have more data. The SaaS algorithm is taking 15 hours, 20 hours to run. And it does not consider social media data because it's built 15 years ago. At that time, there was no, social media. So how do you make a change like this? Or take banks, for example. There's a loan default application. I want to try and understand whether the prospect can actually pay a loan or not. Okay. So essentially, you want to be able to analytically prove the new process is better than the old. I can quote another example, a gaming company where games are recommended. So we came up with an algorithm and said, yeah, this algorithm is much, much better. It is using a lot more data and it will predict a lot more, and it will recommend a lot more games. And those games will translate into income. The business said, okay, we will run it on key days so we can get a comparison of how much more revenue we get, and that's when we decide whether we will want to use your algorithm or not. Right? So the adopt and the run phase are not to be taken lightly, because that's what decides whether this whole initiative is worth it or not. All right. Now we'll go into, how can you do this in the industry? Now, machine learning is maturing. Like I said, there is a lot of frameworks and platforms that are coming in. So you can see Gartner's 2019-2020 ML platforms, and you will identify there are a lot of existing tools like SAS or RapidMiner or K9, and they're all changing in terms of new and additional platforms. So you'd want to keep an eye on what is happening in the tooling space, even though, yes, tools don't matter, algorithms matter, data matters, but essentially you have a platform to build and support. And I mentioned about ML pipelines not run by the data scientists. So this is where I'd recommend, people take a look at ML flow if you have not already used it, or if you've not already looked into it. I find it simply superb in terms of capabilities for orchestrating a pipeline. Essentially, I want to run a simple decision tree algorithm, but I want to sample it on various data, and I want to repeat these so that I can track the efficiency of the algorithm. So this is by far the simplest mechanism. We have built a lot of um, hand-coded frameworks, and then we have to change them 6 months down the lane to incorporate new algorithms. But MLflow comes up with a decent suite that supports multiple algorithms. In fact, you can actually plug in a TensorFlow model or a cart-based decision tree and run the same orchestration pipeline. As I mentioned, once you have trained everything, you have a deployable model. How do you deploy it? So again, I've seen a lot of data science kind of get to a pause here, because now this model has to be part of a web service, which has to be part of a specific API in a department to be able to work. So understanding how to productize your models into services is key. So Dockerized Flask APIs are an easy, understandable way of creating an API. If you're familiar with Python Flask, even better. You just have to learn a little bit of wrappers on Docker. And then AWS or GCP, they have container registries where you put this container in. And what's the benefit of it? You're not running around web service teams to make a service for your ML model. In fact, a lot of organizations that have interest in running ML at scale are preferring a deployable prediction as a service. This year alone, we have deployed dozens of models in this fashion. There is more benefit to it. What if your service needs to run on a different environment? For example, it should run in a car. Now you don't want to code it up in a different language. You started writing it in Python, but the firmware in your car only runs C. So a lot of those are actually taken away by simply using mechanisms like Docker, because you have containerized it, you have packaged it properly, so you can deploy it anywhere. All right. So I think I gave various contexts here. There is quite a bit of information. I understand, but I want to make sure, this is everything surrounding the algorithm, right? With that, we come back to understand what are our goals, right? We started with something called well architected. What does well architected mean? It means the same thing. From goal definition to collection of business data, understanding business data, all the way to deployment, but in operational terms. So you want streamlined data collection. The next thing is version control feature engineering. I built 3 algorithms with 10 features. Somebody else built 4 algorithms with 200 features. Third one is super important. I have seen N teams where there is no collaborative discovery of features, which means from 10 data sets, we picked some random features which are useful, but we didn't leverage or mine the knowledge about our features. That means there is no team effort, very simply. So the next part is distributed training. Again, like I said, training your algorithm on the desktop or a single server may not cut it. So the rest of them we discussed: reliable ML as a service, prediction performance, drift monitoring. So we have to understand when there is performance drift, and model governance and fairness. So, so far I think we're looking very broad and wide. Now, I can anticipate a question like, how many data scientists can do any of this or all of this? And why will they do all of this? They have their problems. They have data and they want to figure out how to solve a problem using that data, right? Yeah, the answer is correct. Essentially, it's not done by a single data scientist or just the data science team alone. But there is enough understanding that needs to be built within data science teams. And that helps productize their algorithms and data products. So you can see data science teams are responsible for conceptualization, prototypes, and they'll get to a design review of their algorithms. There are ML platform teams that actually start doing training and cross-validation independent of the data science teams. And there is API development teams, DevOps, infrastructure, governance, again, back to data science teams where you have to look at model monitoring and model feedback. Let's look at ML development alone. So we start with business needs, market research, business value. What's the value of predicting something? How much benefit does it have in providing this prediction? All the way up to feature engineering training. And I won't go through this because I think this is the part general data science trains people on. Once again, a different way of looking at the same thing in terms of what does ML ops mean. Same story, different slide. Essentially, you want feedback from your model, and the feedback gets to revised training, and revised training leads to more monitoring while managing to understand outliers, any skews, bias, or fairness. All right. So I think I've spoken at length on each slide. There is quite a bit of information, and my intent was to provide the breadth of an ML platform. Um, it would be interesting to play around with a few algorithms and actually get into depth of that. But I think you do that for a day anyway. And what I see lacking in most of the data scientists I talk to is this understanding. So I hope that is helpful. I really didn't plan for 90 minutes. I'll take as many questions as possible.
Sure. Thank you so much, Krishna. So, guys, whatever questions you have, please put in chat box. And Krishna, I would like to tell you that we have a couple of our professors join this talk, and even our data scientists. We have Dr.
Wonderful.
Srirama Murthy also here. So, uh, sir, I think I have given you access to speak, to unmute yourself. If you haven't got it yet, please tell me. I'll do it again.
No, I got it. Thank you very much, Latika. Mr. Leela Krishna, how are you? So good to hear you again. Uh,
Same here, sir. Same here. Very good talking to you after some time.
Yes, it's a pleasure. And I really enjoyed your talk. Very, very pertinent topics. Thank you very much. The question I had was on the concept drift. We see that the frequency of measuring the drift or
Mhm.
frequency of looking into drift differs significantly between projects. If you could please, comment a little on if it is possible to look at what type of machine learning project it is, and based on that, coming up with a reasonable schedule for drift measurement. If you could please educate us on that.
Oh, absolutely, sir. So, like you rightly pointed out, it is very use case specific. That's the reason for it. Uh, for example, I've seen profitability based on loan default or loan interest calculations. And if we are trying to predict that, we could do that pretty much every day because some loan payments start to happen and there will be some default payments, some late payments. So, in terms of predictions, we are looking at something as a basic thumb rule. If your prediction frequency is X, you would want to be somewhere in the 3X range to be able to understand whether your predictions are calibrating soon enough. Obviously, they can only be calibrated based on actual data, which needs to be available for evaluating our prediction. Does that sound reasonable, sir? Hello?
Yes, sorry, there was some issue with
Sure, sure.
unmuting. Yes, absolutely, it does sound reasonable, especially in things like financial applications like the loans you have mentioned, or in healthcare applications where the let's say nature of a flu is changing because of seasonal or other immunity factors. We see that there, the drift needs to be planned well, and
Yes.
that's the context of my question.
Oh,
The only other question I had was on the cost of ML operations. I know that this is slightly peripheral to what you have the data scientist focus that your talk had today. But if you could please educate our data scientists and me on if we are proposing, let's say, if we are making a proposal to a customer, there is a
mhm.
certain amount of cost for the development phase, and there is ML model development phase or deployment, and then there is a certain cost for the maintenance of the models. In regular
Absolutely.
software development, AMCs are sort of standardized now. Around the world, there are different, let's say, a percentage of the development cost that is used for AMC. That doesn't seem to be directly applicable for the machine learning context, where the model management may be a much more involved stage than an AMC. So if you could throw some light on how one should think about, let's say, when estimating a ML project, how one should think about the development versus management stages.
Absolutely, sir. So I think the first part of the question was about concept drift on um, healthcare sector or pretty much unreliable outlier based factors, right? For example, we have a risk of operating cost in some areas. How much risk can you introduce? This cannot be measured directly. So concept drift in those cases, what I have seen, sir, is in terms of building ensembles and trying to replicate scenarios across ensembles to compare across them. So that's another way of creatively measuring concept drift. So essentially, we are not relying on a single ML application, but we are looking at risk from multiple perspectives across multiple models. Coming to the cost and budgeting for ML applications. Again, let me go back and share a few slides so I can share what I had an opportunity to do. So in terms of the cloud stacks, the benefit is you could be quickly self-serve, and for developers, you can start with, or data scientists, you can start with a very small instance type and scale it as you go. So that's an important consideration we provide. In fact, this architecture is something entirely built with my help. And in this architecture, I have some data wrangling with Jupyter Hub, and there is an EMR cluster. So we started with very, very basic what is needed. And the benefit of the cloud is you can always auto scale and adjust for the business value and budget. Production will be obviously a slightly harder ball game to predict. What we start to do there is take the amount of data into consideration. And if we are looking at boiling the ocean use cases, the business value needs to be projected much ahead of time. So in case of this platform, essentially using EMR Spark, we could start, I mean, Spark can run starting from 3 nodes. And as you guys probably are aware, for the rest of you, it allows you to run distributed algorithms, and then there is support for MLib or TensorFlow. So essentially, you start with a minimum number for development and build production with something like the estimated value of the data that's coming out. So for about a terabyte of data, I had the opportunity to build something with 12 nodes, and it did not cost significantly high. At EMR, I mean, to just quote actual numbers from AWS US West regions, it costed about $10,000 a month. But we were able to train with a terabyte of data almost daily. So I think putting together these numbers and projecting business value has helped us, sir. So did I come close to answering this?
Uh, Absolutely. Again, there was some problem unmuting. Thank you very much. It was perfect.
Sure, sir. I can take more questions.
Krishna, we have questions in chat box. If you could please open the chat box.
Okay, let me check.
Yeah.
So how different, go in the order in which they came, how different is the architecture of real-time data, for instance, for ML for onboard systems of aircrafts or automobiles? Oh, wow. Okay. This is a really good question, a question of interest, because I'm working on automobile systems at this point for a company called Omnitracs. What we do is essentially either attach a device to a vehicle or have the driver carry something like an iPad. I mean, if you have seen package delivery workers, you may have seen that they carry a signature pad device with them. So either of those devices will be used for gathering additional insight. And deployment is slightly more phased. So it's not like your typical web architecture where you can write a service and deploy it there. Now you have to work closely with the firmware team, and they have limited schedules because one of the key challenges I run into is I have some code base always ready. There's always a next version of improvement, but I can't push to firmware every time. The best closest example I can give you is your Android or an Apple iPhone. Apparently there are at least 2 billion Android devices, or even more. I don't know track of the count anymore. So if you have to upgrade everything from Android 5 to Android 6, how long does it take? This tends to be a very interesting question because you don't know that all these devices are first of all turned on. They are charged enough to be able to deploy. So where I'm coming to is deploying in embedded systems or in real-time systems which are outside of your data center or cloud premises is a much more phased approach. I hope I may have answered that. As such, from the software perspective, yeah, sometimes you are limited by, okay, you have to change this algorithm, deploy it only in C. Sometimes, in fact, there is one case where we developed everything in R, then we had to change it to MATLAB because it was more convenient for them to run MATLAB based algorithms which have C code gens. So I'll take the next one. How do I ensure the robust model prediction quality? For example, in case of image label prediction, model says a specific image is predicted as label 1 with 100% probability. However, the label could be incorrect. Fantastic question. Okay, so there is there is no better predictor or auditor than a human in case of images. The simple answer is have some humans verify it. Again, I'm talking about general cases. Let's say like identifying street signs, etc., that we did. We had to put together a team. There are actually vendors who can put together teams today. If you Google for object detection tools, you will actually find there are companies today that will provide an object detection algorithm, and they'll also have a manual human team that validates these labels. So, I mean, your curiosity is right. The algorithm or the code base itself will never be able to do label prediction or labeling itself correctly. If, again, I gave an example of Bing, right? Both Bing and Google have more than 1,000 human auditors for the search results and the quality of search results. Simple reason is you can't just allow machine learning to go in on something as heuristic as such. One more question there. What are the guidelines one should follow to realize that model started failing and time for learning? Really good question. So this is about concept drift that we were talking about. Essentially, model performance, you all learned that model performance is measured using bias, sensitivity, recall, the confusion matrix, right? But what happens is people tend to forget you have to track confusion matrix across training cycles. You have to go back and take whatever is predicted in production, bring it back, treat it like training data, and publish ROC curves. So the industrial side of it is not done very well, and that's not for reasons that data scientists are not doing their job well. It's just that other people don't understand data science. When they deploy a prediction service, they think it's exactly as binary as um, a regular software engineering service, which tends to be more predictable. So maybe I'll simplify this. Instead of a very broad answer like this, I'll say simply log every prediction with the input data, take it back to your training data set. See what's the difference. You will be surprised. Sure. How do we deal with retaining the model? I mean, what do you change in the model to get better performance in case of your example drop from 4% to 3%? Yes. So it's a tough question, right? I mean, so there is nothing that says, oh, 90% of the model is right. You add just this additional parameter and you will be back to 4%. That's where entire feature engineering, PCA, all of those come into play. my advocacy in today's session is only for us to version features better, right? I have an algorithm one that I have trained with a data set from, elements D1 to D255. I can use n permutations and combinations with a new set and then track algorithm with the training cycle T2. That's why I tried to show ML flow. You guys should try ML flow, because back then we didn't have ML flow. And if you're dealing with some data sets like Omniture, the click-through rate data sets, they have like 2,500 features. Right? So I understand the goal here in terms of what do you change, but that's the whole game of industrial or commercial data science. One more question. Of the vast skills, what are data science skills one should focus on for a fresh engineering student um, and a student with say 5 to 10 years experience already in data science? Okay, skills is an interesting thing. I mean, let's not forget the concepts are the same. So whether it is Statistica or SAS, we've done the same thing time and again, right? At the university level or even with cutting edge algorithms. Neural networks, TensorFlow, PyTorch will show a few variations of it. At the end of the day, we need to understand what the algorithm is doing in some form or fashion. So, I mean, my answer for skills is we have to keep upgrading with the industry. If we have to get to H2O and sparkling water and TensorFlow, we have to, right? There's no set skills that we need to get except for the basics. Like if you know your R and Python, and if you're able to properly train and deploy algorithms, that's a good starting point.
Right. Do we have any
Right?
further questions?
Yeah. So, hey, Krishna, this is Venkatesh. Can you hear me?
Yes, absolutely.
Hey, thanks. Hey, thanks for joining. Appreciate it. And I'm sorry I couldn't attend the whole lecture, but I was enough part of it. Excellent. Thank you very much. It was a very informative lecture. I really appreciate it. So I had a couple of questions, or maybe, it's a two-part question. The first question is, and I'm sure, is, see, there is, and you rightfully said, right, most data science, because we do quite a bit of projects, not a lot of projects in INSOFE. One of the things that we always struggle, and you rightfully said, is it's not the algorithm part, it's the deployment part.
Mm-hmm.
So basically, how do I scale? So I have done with X, training data. Now I have Y, which is the real-time data, which is 10x X or something like that.
Yes.
So basically, you said about, so the question here is, is there so the question basically, when I do my training data or when I develop my algorithm, are there any things I need to think about to basically at the algorithm phase? Then I'll come to the deployment phase, where I need to start thinking about, whether these things I have to do something special to say, hey, make sure that if your algorithm does this, it may not scale to this. Are there any tips and tricks in your thing that you can say at the algorithm phase, so that when I take it to the larger thing, that scaling happens?
Absolutely, sir. That's, I think, a wonderful question. For those of you who are from computer science, you got a taste of it, but you probably didn't realize the power of it, right? I mean, I'm talking to the context of students, right? There are certain things, I'm lucky enough to have found them at some point in the career. So I'll write it down. So, I can't stress the importance of these. So the first thing is called BOAT, which means back of the envelope calculation. Right? So let's say we are doing something very elementary, 1,000 rows in an Excel sheet. I have tried to train it. The things that I track apart from the actual data science metrics, I would track some software metrics. How long did it take to train 1,000 rows? And by extrapolation, how long would it take to train 1,000,000 rows, 10 million rows, 100 million rows?
Exactly. Yeah.
Simple multiplication at this point. It's called back of the envelope calculation, right? The second one is very similar. It's called Cube. It's actually from IBM, and Sriram Murthyar is here to probably elaborate on this as well. It's called quick upper bound estimate. This is a popular philosophy, to talk about algorithmic questions. So let's say I want to build a bank, which means I'm actually building the systems behind the bank so that somebody can run a bank. Again, you start with board and say, okay, how many ATMs do we have? How many tellers do we have? How many cashiers do we have? Ultimately, how many transactions do we have to support? As I mentioned in the talk, I'm not sure if you're there at the time, sir. So essentially, we had a privacy need for some drivers who are in front of the camera. So one of our data scientists said, oh, that's very simple. We have a CNN. I'll block off the faces. And then we found that the throughput was only 1%, which means, I mean, we are able to block off faces, process images at like 4 to 5 images per second. And what we were getting in the inflow is more than 250, actually 300 images per second. So having this knowledge early on, understanding that you're only able to train 4 to 5 images per second becomes super important when you go to deployment phase. And if you want to read more about this, mostly for the students, right? There's a really good book. It's called Programming Pearls. A lot of people struggle with algorithms, even in computer science, right? That's probably the most boring subject for quite a few people that I know of. Instead, if you read Programming Pearls, you will actually intuitively pick up algorithms, right? Don't look at binary search as binary search. Look at it as a way to cut down your search space fast enough at an exponential rate, right? That's what I've seen Programming Pearls teach. In fact, it's become so regular that we actually gift this book every quarter to one developer within our teams.
Yeah,
So,
thanks.
I hope that
yeah,
that
very
answers.
useful, right? Because see, to be honest, right, one of the things that we are facing today, and honestly, because this is since you brought up, right, that when we train the data was there, but as you rightfully said, now when I'm trying to deploy, they're saying, you know what, the data is encrypted. We never planned for the encryption part.
Yeah, absolutely.
So now I have to deal with encryption and decryption, which we had never planned at the training and the tuning part.
Yes, I mean, I can share more in this context, sir. So when we are dealing with the data problem, again, this is customary of data science teams, right? All they care about is data. I recently came across a case where we said, we're going to predict market value of vehicles. Oh, beautiful. Some vehicle is used. Now I want to know what it costs compared to a new vehicle. If you predict it, you know how to sell it for a reasonable profit. And they got the algorithm and everything, and they started working out all the details. The only problem at deployment is this data was gathered, and I'll tell you some of the indicators there. There is a Moody's recession indicator, which is obtained from Wall Street's public data sets. There is DMV information, which is driver's license or RTO office information from the vehicles. Now, how do you take this to production? Do we have all of this data in production? I mean, and the answer was no. So we had to cut down our features, make sure we can compensate. Sometimes, in case of vehicles, we can actually, in the States at least, you can get vehicle tracking information, vehicle history information with additional budget. So things like this. I mean, in research space, it will be easy for us to gather public data, but when you go to production, you don't have a way to formalize that.
Excellent. And so that's, and my last question is, now I come on the deployment side, so that, you know, that's another part of it. So now we are gone to algorithm. In the department, as you rightfully said, right, there are a lot of sources of data that goes into my, you know, the deployment framework. The question is there are tips and tricks, or ML flow takes care of it in order to speed it up, basically to say that, you know, should I do a lot of pre-processing first, or is that something ML takes care of it, so that, you know, if I have vast sets of data, how do I collaborate all the data so that end of the day, what people are saying is, what is my prediction time, right? I give X,
Yeah.
I want Y, whatever that Y is prediction time.
Yes. So if you have various data sources, again, you know, typical data scientist focuses on getting his data on an ad hoc basis. You know, the trick I would say is just blame your data engineering to give that. Let them sign up for providing you data, right? Because they have systematic pipelines to provide data. Like we see here, if you pull data into Jupyter Hub, it is your responsibility on how you are pulling from here. But once you do that as a sample, sign it up to some ETL team within the company, they will be on a contract to provide you this data every hour.
Okay.
So that's so
yeah.
half of data science deployment is actually collaboration with other teams.
And last question, and I apologize, is there a way for me
absolutely.
to streaming data versus static data? Is there some tricks or tips? I just wanted to ask that.
Sure. So let me answer this two ways. So can we accumulate streaming data? Do we really need it streaming is one question.
Really need it in real time is what you're asking. Yeah.
Yes. So that becomes an interesting question, because I've seen a lot of people use Kafka. They don't have a real-time use case. They are just consuming because the data is in Kafka. What I have done in some cases is you write a simple S3 connector to Kafka. Every 5 minutes, you get an Avro data set. That's more than enough. Right? So this is one side of the story to really test out our use case for streaming needs. The second one is a little bit more challenging. You deployed this algorithm in a car, live data is coming from the vehicle. Now you have to do some prediction. You calculate moving average, as simple as that. No machine learning algorithms. Simple moving average can only be done with streaming data in some fashion. So in that case, you would need knowledge of some streaming framework and the endpoints and how do you poll data, right? Simple patterns like publish and subscribe, or polling data from HTTP endpoints. So that knowledge would be useful, sir. In this case, you would see there is sometimes there are kinesis pipelines, which is basically you know, a framework that can give you streaming data. So adopting something like that would be helpful.
Hey, thanks a lot. Appreciate it.
Sure.
Thank you, sir, for asking these questions for the benefit of participants as well. And any more question? I think we have another one from Jagan. Krishna, if you can take up this last question. Yeah.
Sure. What are your suggestions to estimate the impact of events such as COVID-19 on jobs and markets in general? We do not see an event can happen, but impact is so severe. Yeah. I mean, I think this is a budding field in even most mature industries, right? How risk averse is the business model is something people rarely question. They're into production, they're producing something, they expect it goes through the supply chain and it gets sold happily. And this is where shock comes into play, right? I know at least a few teams where we are doing risk analysis, risk management work. In fact, you have seen it here probably. There is simple risk marts which are just built for this. Introduce an unpredictable amount of risk and see what happens. Right? And when it comes to jobs, I think it's a different paradigm, right? This is something LinkedIn and of course the actual prospective employees should be worried about. There is no direct way for us to predict how the job market gets impacted. I'll give you an example. Typically, when recession happens in the United States or in the European region, I've seen counter effects in India and Asian region. Because of cost cutting, there will be more jobs in the other parts of the world. But I think from a data science perspective, what I'd say is some level of risk and outlier analysis is absolutely important, right? It's not thought through and it doesn't pay back. The reason people don't do this is what's the business value? Who's going to pay for all of the effort that I put into this? So that's I think that's where you'll need more attention. Similar to like software systems, right? Most people, they deploy systems and they don't actually test for crashes or business continuity. But it's becoming a mature practice now. It's called chaos engineering in the software world. Sure. Thank you.
Yeah, we really did enjoy your session, Krishna. Thank you very much for accepting our request. I know that you are on a business trip, and even, I mean, despite of that, you have taken out time on my request to share this vast knowledge to our students. Thank you so much again. And really appreciate the fact that you have, very patiently you are replying to the questions. Thank you so much.
Yeah, I mean, so I mean, we can discuss some of these things now, or we can go to the industry and find out a year later. It's the same thing, right? Time and again, sharing this with academia actually helps us.
Yes.
And like I said, this this is also equal passion for me. And
Right.
we're working with Triple IT Hyderabad and a few colleges in Bangalore. Um, the benefit is mutual, I feel.
Yes, certainly,
Thank you
certainly.
for the opportunity.
Pleasure is all ours, and we will definitely look forward to having you again with some other topic of your interest and choice. So, sure, we'll
Sure.
keep in touch. Yeah.
Thanks,
Thank.
Nitika. This time it won't be a PowerPoint, I promise.
Yes, definitely in person.
Sure.
Right. And thank you to all the participants for joining this session and making it interactive. Thank you, everyone. Take care. Bye bye.